Um, Hello everybody, this is Dr. Hassan again in Digital Introduction to Digital System. Still talking about the topic number systems. Here today we'll talk about more numbering systems. Okay, last lecture we started with decimal, binary, and mentioned to octal, and today we will discuss the hexadecimal numbers and how we can convert from binary to octa or octa to binary and hexa, so on, and also conversion between these systems. Also, we will talk about the value range of numbers and how we represent positive and negative numbers, and then creating the complement of numbers, which mainly used for negative um, numbers, dealing with negative numbers. And finally, why binary? Now, just to remind you regarding last topic, where we define the bits to be one number, either 0 or 1, we call it bits, okay? And also, I would like to remind you with how we convert from binary to decimal, as you can see here in this example, okay? This is binary because the radix here is 2, and here 10, so this is decimal. And we convert them by take each one of these number, this one and this one and this 0 and this one, and multiply by the power to the unit of place. For example, 2 to power 0 by 1 to plus 2 to power 1 and so on. Now, for fractions, the same idea applied here, but for decimal, this one, the fraction, we multiply by 2 to power minus 1, minus 2, minus 3, and so on. And if we put 8 numbers together, or 8 bits together, we call them byte, and a group of 4 bits, we call them nibble. Okay. Now, let me talk about the other numbering system, which is hexadecimal. Hexadecimal, remember, binary is 0 and 1, so 2 numbers. Octa is 8 numbers from 0 to 7. Decimal from 0 to 9. Hexadecimal, we have, you can see here, from 0 to 9 and A, B, C, D, E, F. Now, you may ask, what is A, what is B, what is C, D, F, E, F? Now, we approach to 9. Now, A represents 10, B 11, C 12, D 13, E 14, and F 15. Got it? Great. Now, see how it look like the hexadecimal number. It's written this way: 3A, A9, F. I take them one by one. Now let's take F. F is 15, right? Don't forget F is 15. Multiply by 16, you see the power, the text, to power 0. Now 9, as you can see here, multiply by 16 to power 1. A is 10, right? We say this is A, right? Is 10 multiplied by 16 to power 2 because the place is 2. And last 3, got this 3, 10 to power 16 to power 3. Now it looks like there's sort of similarity between conversion in binary, in octa, and decimal. Okay, we multiply by the radix. Now I use the calculator to find the results. It will be decimal value, which is equivalent to this. Easy, right? Thus you need to remember A, B, C, D, E, F are 10, 11, 12, 13, 14, 15 respectively. Now what about a fraction? The same idea. Just you see here, after this point we have 5, so we will multiply 5 by 16 to power minus 1. Use the calculator to find the value here. Easy, right? So it's the same procedure in all systems we discussed up to now. Note that each hexadecimal can represent in 4 bits, because 15, we say here that the last number, the highest number, let me say, in hexadecimal is F, which is 15. So it's kind of represented, as you can see here, by this presentation. Okay. Now, example here as example E. E, how much E? E is 14. Agree? Okay. I can write it 0, 1, 1, 1. You see here, this one represent 2. This one represent 4. This one represents 8. 8 plus 4 plus 2 give me 16, which is E. 14, sorry, which is E. You got it? Okay. Now this is conversion from binary, as you can see here, into hexadecimal. And don't forget that 4 numbers together, we call them nibble, okay? Now this is a comparison between the 4 systems: decimal, binary, octal, hexadecimal. As you can see here, decimal 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we started 10, 11, blah, 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 and so on. What about binary? 0. Then we started with 1, with 2. 2 equivalent to 0, 1. 3, 1, 1. 4, 0, 0, 1. 5, 1, 0, 1. Okay? And you don't need to write it on a paper now, because you remember that the first number to the right, which is the least significant bit, multiplied by 2 to the power 0. The second number, 2 to the power 1. The third number, 2 to the power, and so on. Okay? It's easy to convert from decimal to binary, vice versa. The same thing for octa. Octa from 0 to 7, and then from 10 to 17, from 100 to 717, and so on. You can see here also the hexadecimal. From 0 to 9 is clear, and then from A to F, these are the remaining numbers. Now, conversion between 16 and binary, which is base 2, is easy. Have a look. You see here, this is 3A9F. Okay, we're supposed to start from F, F9A3. See, the base is hexadecimal, 16. So I take them one by one. F, which is 15, represented by this number for the base 2, which is 1, 1, 1, 1. 1, this one, plus 2, plus 4, plus 8, altogether 15. Now let me take the second number, 9. You see here, 9. Okay, it is 1, 0, 0, 1, because this is 1 and this is 8, it's 9. Let's take the third number, which is A. A is 10, right? So this is 2 and this is 8, it's 10, right? 0, 1, 0, 1. And 3 is 1, 1, because this is 1, with this is 2, 3. You see how I wrote it? So at the end, hexadecimal represented in binary by 4 groups. Each group contains 4 bits, right? Conversion is easy, as you can see here, 4 bits value for each hexadecimal. Okay. Now, what about converting to base 8? To base 8. Have a look. This is the number in hexo. This is in binary. Okay, and you see here it's octa. Octa, if I want to convert it, this number equivalent to this number, right? Equivalent to this number. Anyway. You see here, base is 8, which is octa. Okay. Now each number represented by 3 digits, because don't forget that octa, the highest number is 7. 7 is 111. As you can see here, this is 7. 111. 1 plus 2 plus 4, which is 7. And now the second number, 3. Okay. 3, 1 plus 2. And the third number is 2, 0, 1. The fourth number is 5, 1, 0, 1. Okay. The third number, the last number is 3, 1, 1, 0. You see? So each number represented by 3 digits. Okay. This is how we convert from octa into binary. Now, the second issue here I would like to discuss is the sign. I mean, we know that some numbers, some of them are positive, some of them are negative. We know how to represent them in decimal. As example, we can write 25 plus 25 minus 16 and so on. But computer need a new, different way to understand, because at the end it's dealing with 0, 1. But it need a way to understand the sign itself. If it is negative, if it's positive, is easy, but negative, the issue is an issue. We have 3 types of sign binary number. One of them is sign magnitude, and I mean the way of representing. And the second way is 1's complement and 2's complement. Okay, I will discuss these methods. Okay, in each case, by the way, leftmost bit indicates sign. I mean, as example here, this number, you see this number in binary, which is equivalent to 12 in decimal. the last number here represents the sign. Okay, if it is 0, this means that this is positive number. As example, 12. This is also 12. You see the same number, 0 0 1 1 0 0 0, but the last number is 1. 1 means it is negative. Got it? So sign magnitude is very easy. Look to the most significant digit. If it is 0, it means positive. If it is 1, it means negative. This is the first method. Now let's go to one's complement presentation. One complement presentation is done by inverting all numbers. It means like putting inverter. The number came, if it is 1 it becomes 0, if it is 0 it becomes 1. You see here this number? Okay. Now if I want to find one's complement, then 1 become 0, 1 become 0, 0 become 1, 0 another 0 become another 1, and 1 here is 0, and 1 here is 0, and these two zeros become two ones. You see here I invert everything. This is called one's complement. Okay, another example here. I don't think it's difficult, it's easy. Just convert 1 into 0, 0 into 1. Done. And this example here, see, similar to the previous example over 12 and minus 12. You see here, this is 12. Okay, in one complement, one's complement is, see what I will do for negative. Okay, this 0 become 1, another 0 become 1, two ones become 0, and all zeros here become ones. When all of them become ones, you see here what this 1, what does it mean? It means it's negative number, right? So we write it minus 12 10 to the base 10. Now another method is 2's complement presentation. 2's complement presentation is based on 1's complement presentation. It means if we have number, we apply the 1's complement presentation, as I said, invert everything, and we add 1 to the least significant bit. Example, see this number? This number, when I want to find 2's complement, I will convert all these numbers to the opposite. I mean, it will be 0 0 1 1 0 0 1 1.